Good morning. Let's continue our discussion of probability as it relates to statistics. Last time we talked about expected value, and we talked about how you can combine multiple lists of numbers and their standard deviations and mu's into combinations through a linear process. We talked about, I think, an example dealing with sorry for that. We talked about an example dealing with life expectancy and insurance, and we also talked an example dealing with the stock markets. Today, what we want to do is we want to focus on a little bit more specific of an example that's a little less varied. And that is binomial probability. Binomial probability has at its heart the idea that unlike last time, where you could buy multiple stocks and put them together, or you could have had the CEO at 35, 36, 37, 38, and 39 if you had a 4-year horizon for your company. We oftentimes live in a world where there's only two possibilities: win or lose, success or failure. Now I should be careful here. If you read your book, you will see that it talks about binomial probability as success or failure, and that's nice. But you have to keep in mind that we define success not to be some rosy Emerald City type process of success, but instead we define success to be accomplishing the objective that we currently say we want. So for example, let's say for me, because I'm a medical researcher studying H1N1, success will be finding people infected with H1N1 who I can study. That's not a very nice thing to call success, but from a statistics perspective, it makes sense, because I need to find people who have this disease before I can cure it. So, what we have is this idea that we can have win or lose, pass or fail, success or failure. Here's some criteria, though, that we have to keep in mind always before saying, this isn't just any probability distribution, it's a binomial probability distribution. Here's what we need to have. And I think that we have this labeled out as 5 different steps. So let me go ahead and put them in 5. Everyone has a slightly different head count for this, so let me make sure that I'm putting them successfully into 5. The first thing we have to do is there has to be a fixed number of trials. And it suddenly occurs to me with this prevalence of hashtagging that everyone does, that possibly the original use of the hashtag as this idea, the pound sign really, as a substitute for the word number, might be getting lost. So I'm not hashtagging on the board, I'm putting a shorthand for number. I do hashtag quite a bit. For example, I could say hashtag awesome professor, hashtag mathematics. And now you're like, yeah, that was lame. And if you were my face-to-face class, I would talk to you about laughing at my jokes, and I would say, no, there's this punchline, and then when the punchline happens, the students laugh, and it's very funny. But anyway, we need to have a fixed number of trials. When you're doing a probability distribution, what you can't do is have an unknown number of attempts. So if I want to find people with flu, I have to go out and say, I'm going to check 10 people. I have to commit. If I want to talk about binomial probability, I always have to have a very specific number of trials, because n is locked down from the start. The next thing that we have to do is these trials have to be what we call independent of each other. What does that mean? It means that what happens on the first run of the trial doesn't influence my second run. Those are separate in some meaningful way. So I can't have a scenario where, let's say, the first trial that you run is some kind of long jump, and the second trial is a follow-up to that long jump, because maybe in the first trial of the long jump you could break your leg. And then obviously your chance of success in the second one diminishes drastically. We don't want to have those chain effects. Now, of course, anything could possibly go wrong, but for example, independent would totally be 5 questions on a multiple choice test, because you've got a fixed number of trials, the 5 questions, 1 for each question, and your ability to answer question 1 correctly really has nothing to do with your ability to answer number 2 correctly from the perspective of the problems. Now yes, if you didn't study at all the night before, you probably wouldn't get any of them right, but if you focus in a little bit more and say, whether I get problem 1 right or wrong, that has nothing to do with me getting problem 2 right or wrong. as far as problem 1's concerned. It's not like problem 1 can stop you from getting problem 2 correct. So they need to be independent. The next thing we talk about is that there needs to only be 2 outcomes. There's this root word bi in here, and bi means 2. We talked about bimodal earlier, so there needs to be 2 outcomes only. Now let's think about a multiple choice question. Let's say I have the answers A, B, C, D, and E as my possible list. I can still group that into the 1 correct answer and the 4 incorrect answers, and so I can force that to be a 2 outcomes only scenario, even though really you could have lots of different answers. And it would depend how I modeled the problem, whether I would use the problems from 5.1 and give 1, 2, 3, A, B, C, D, E, or whether I would lump them together and talk about this binomial concept. We can sort and organize our models in different ways. I said this maybe very early at the beginning of class, that it's the difference between drinking a glass of water or trying to drink a whole ocean. There's a sort of limit to how far you want your models to go. And for us, we could choose to model a multiple choice question, all 5 parts separately, but we might say, you know what, it's easier to group it into right or wrong. So 2 outcomes only is a requirement that we have. Another requirement is that it has to be the same each trial. Each trial has the same odds. What do I mean by that? I couldn't have a multiple choice question of A, B, C, D, E and then have a true-false question over here, because the chance of getting into the right or wrong categories on each of those is different, separate, and that's not fair. So each trial has to have the same odds of success or failure. We call those odds P and Q, and so as you can see from our formula, I don't have spots for multiple P's and Q's. We've only got 1 P, 1 Q, so they has to stay the same for each trial. And then, finally, for part 5, this idea is we're trying to find our successes, the chance, the probability of our successes out of n trials. So we want to find out how many successes do we have after I've tried so many times. Got your number R here. R equals number of successes. So fixed trials, independent, only 2 outcomes, win or lose, pass or fail, success or not success. Each trial has the same odds, you can't go changing up the scenario, and the chance of success of our successes out of n trials is what we're trying for. So having said that, let's take a peek at this example. A professor knows the chance a student will not attempt the homework is 20%. That seems a little steep, but in my experience, that's about right. Students don't log on to the online system. For all of my classes, at least the first 14 days are free. And you'd be surprised how many students choose not to register, not start into their homework, and so at least the first 2 weeks are missed by, I'd say, upwards of 30% of most students. Get into the homework as soon as possible. Find your success. Get that practice happening early, and you'll set the tone for the whole semester. Still, 20%. And I'm not talking about a single assignment. I mean, pretty much, I expect about 20% of a class to never really do their homework. And under the grade scheme that you'll find in any of my syllabi, that's a very big risk. In a class of 33 students, if I know this number of success chance, and notice, once again, here's a very odd word for success. My success is 20, and success is a student not doing their homework. But that's what I'm trying to look at. You could flip it on its head and say there's an 80% chance that they will do their homework, and you could look at the problem from the other side. But truthfully, if a student's doing their homework and scoring above a 90% on it, life's pretty good, and I'm probably not going to try to really grab that student in any way, because I'm going to say they're doing a good thing. I don't want to impact their success. Whereas it's the student who's not doing their homework that I need to kind of focus on and figure out, what can we do to make this work? Why would someone choose not to do the homework when that creates the quizzes and that creates the midterm and final? So we have these kinds of questions that we want to ask. What's the chance that at least one student in the class does not complete their homework? Because there's of course always the chance that maybe this class will be perfect. Everyone. Every student always does their homework all the time. That would be fascinating and I would be thrilled. What's the chance? Well, we can figure out that or put it the other way. What's the chance that I have at least one student that we have to try to have this conversation about? Please do your homework. It's how you're going to succeed in the course. Another question, and kind of that's the flip of that, what's the chance that no student does not complete? And notice we've phrased that strangely. In English, double negatives aren't recommended in terms of grammar. However, in math English, double negatives are fine because we can figure out how they cancel. So we can rephrase these things a little bit, and that can make it a more natural question to ask. But this is the way we think of this question in math. So let me actually turn this question on its head. What's the chance that no student does not complete? First, how would we say this in English? No student does not. Those cancel out. Remember, -1 times -1 is +1. So student does complete. What is the chance that all students do their homework? Incidentally, this probability distribution can be used for a lot more than me figuring out today, right before the semester starts, of how likely I am to have the perfect semester. Because you can do a little bit more. I can say not only how likely is it that this is happening, but if I see this seem to start to happen, then I might start to get suspicious if it's a very low chance of this occurring and saying, what happened? What changed here? And maybe the answer is, you thought all the students were doing the homework, but secretly 10 of them never even registered for the homework product. And so you didn't notice their names listing here. It's time to go back and check the roster. So you can always have some ways to interpret this stuff. But question B really is, what's the chance that all students do their homework? But since we're focusing this on the perspective of 20% don't, remember our idea of success and failure is different. In its own point of view, you can subtract from one and change any probability that you want to the other perspective. But just be careful when you're working the problems in this section that you are very clear on how are the probabilities given and what do we actually mean by success. Keep your point of view correct. Much like last time we talked about expected value, and you could either have a $334 loss for the insurance company or you could have a $334 expected profit for the small startup company because they were thinking, well, our CEO could die and this expected value of this is 334 before they started getting charged money. Let's take a look at this problem. Does one student control another student? Well, you could possibly argue that yes, if you've got a class and they all have an awesome work ethic, that can be infectious, and I imagine probably the other way around. But overall, in general, I would say no. If one student is doing their homework, it's not like they're looking at the other students around and be like, if you touch that homework, I'm going to punch you. So I would say that we do have a fixed number of trials. There's only 33 students in the class. It is independent. You doing your homework shouldn't really stop me from me doing mine. 2 outcomes only. Either the homework's attempted or it's not attempted. We're not talking about the scores. Yes, I recommend scoring a 92% on your homework, and if not, coming to office hours. But in the end of the day, either this homework is opened by the student and the student gets into it, or it's never even touched. Each trial has the same odds? Well, yes. I don't know any individual student before I meet them. So I have the population average of 80% chance of the student doing it, 20% chance that the student doesn't. So each trial does have the same odds. And we are definitely talking about chance of success versus the chance of failure. And in particular, we're talking about a certain number of successes out of this locked number of trials. So this fits our 5-step checklist. It's a binomial problem. So let me go ahead and erase this checklist and let's start calculating. Here's the problem, and it's not a problem, it's just a potential concern of mine for part A. The chance that at least one student does not complete. This probability formula, which notice this piece right here is the combination formula, so sometimes you see this rewritten as NCR, P to the R, Q to the N minus R. But either way, this formula is designed to tell me a probability for one and only one particular number of successes. English has this unfortunate tendency to use these kind of weasel words, at least one. What does that mean? Well, it means one student might not complete, or two, or three, or four, or five. And this gets to be very painful to me because the way my formula is set up, if I count p of 1 and plug it into this formula, I only know the chance of exactly one student not completing their homework. So if I'm curious, what's the chance that at least one student doesn't complete, then I also have to calculate the chance that 2, the chance that 3, the chance that 4. You start to see the problem here. With 33 students, I've got to keep on going until I reach the end at 33. And I've had to cram that in there, but you get the idea. I don't actually get to write plus dot 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 because plus dot 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 doesn't type in numbers into my calculator for me. I will have to calculate the formula that we've just developed 1, 2, 3, 4, 5, 6, all the way up to 33 times, and then I have to add those 33 numbers together. And that sounds painful. Now I could use Excel. That's one option. I could use on calculators that maybe aren't ours, that are kind of lame. You sometimes have some clever buttons there. That's also possible. But there's also a more elegant process that we can do, and regardless of what calculation method you use, this elegant method is going to save you computer processor cycle time, which isn't a problem for 33 calculations, but it is a problem for 659 million calculations. We'd like to save ourselves time. So let me redraw this just a little bit so that I've got some space now that we got this idea that we're going to have a lot here. Always, the total chance of something happening is 1. So I know that p of 0 plus p of 1 plus p of 2 all the way up to plus p of 33 equals 1. If I want to calculate all of these, I can do that by calculating them one at a time for 33 different times and adding them up, or I can subtract the probability of no students not completing their homework from both sides of my equation, keeping the balance of the equal sign. I minus from the left, I minus from the right, and that leaves me on the left this number, which equals 1 minus p of 0. I could add 33 numbers together, or I could do 1 minus p of 0. Calculate one binomial probability and do 1 minus that answer. The right side is a lot faster. And what if I wanted to do at least 2? Well, I could do that as well, because I would subtract off p of 1. And I would have this piece. And so I would have 1 minus p of 0 minus p of 1, and I have to calculate it twice and do that subtraction. But still, I would leave the bulk on the left, and I would just have them nicely automatically summed for me once I did that subtraction. And your book has a couple of charts that go into that for a couple of different scenarios. But you can see the power and usefulness of this. Think about this. If it makes sense, great. If this is not making sense to you, come and see me in my office right here, right now. And obviously you can't jump through your monitor, but make the next office hour that I've got, because this is going to be a very powerful thought process to be constantly saving you calculation time throughout all the rest of the stuff we do. So think about that and make sure that's happening. All right. Notice that to calculate this for at least 1, as I originally suggested, we need to calculate p of 0. But what is p of 0? It's the probability that no student does not complete their homework. Well, that's part B. So actually, if we think about part A in more clever ways, we realize that we should do part B first. So let's go ahead and calculate this out. P of 0 equals what? Well, our chance, our number of successes that we're after is 0, so I'm plugging in 0 here for R. Our total number of trials is 33, so let me go ahead and start to fill in this list of numbers. We have 33 trials because we've got 33 students in the class. we're curious about 0 successes. Remember, success is an odd thing in our world. It's students not completing their homework. We know the probability of that success happening. It's 0.2, which means we know the chance of that success not happening. 1 minus 0.2, which we call 0.8. So now we can plug all these things into the mix. I've got on top 33 factorial. We've got r factorial, which is 0 factorial. Remember, that's 1. And then we have 33 minus 0. P, which was 0.2. And that's raised to the r, which is 0. And we have Q, which was 0.8. All raised to the n minus r, which is 33 minus 0, which maybe we just call 33. This is the chance of no student not completing this. Now, I could notice here that 0 factorial is called 1, and 33 factorial over 33 factorial, and 0.2 raised to the 0, any number raised to the 0 is always going to be 1 as well. That's just algebra. And these, of course, cancel out, so I really just have 0.8 raised to the 33. If you grab your calculator and hit the on button, you can have 0.8 typed in here, and then we have this exponent button here, and I hit that, and then I type in 33 and hit enter. When I do that, I get a very small number, 0.0006 with rounding. So I'll write wiggly equals here. Highly unlikely. The chance that no student does not complete their homework is 0.0006. If I do 1 minus that number, I'll find the chance that at least one student does not complete. And so I do 1 minus 0.0006, and I get 0.9994. Again, this is with rounding. Possibly I round that up to 0.99. I am almost 100% certain that I will have at least one student in that class who does not attempt their homework. The odds are against me. 20% is simply too high. What can we do with this? Well, we can change this problem around a little bit for binomial probability. One thing I could have done, if I hadn't had all these zeros in the mix, this would have been a little more complicated to calculate, and so using the NCR button on my calculator might have been nice. Again, as a reminder, the NCR button on your calculator is right here. And so you can hit it. So if we wanted to calculate P of 0, notice what we would have been plugging in. We would have been plugging in 33, choose 0. And so on my calculator, I would type in 33. You'd hit this choose button a couple times till NCR showed up, and then you type in 0, and then you could hit this enter button down here, and it would give you your answer of 1. And that's what happens when you cancel these out. You have 1 times this, and at the end it's 1 times 1 times 0.8 to the 33. So if we chose different numbers, because we could ask all sorts of things, what's the chance that exactly 5 students are going to not do their homework? Let's say I want to have a bet with my coworkers. And we calculate P of 5. Remember, the key thing for binomial probability, you have to make sure that you've got yourself a fixed number of trials. N can't change. You've got to make sure that as you're looking at this process, that these guys are independent. Success for one person doesn't force success or failure on the other person. You've got to make sure that you only have 2 outcomes, and that can either happen naturally with completing or not completing the homework, or we could make it happen unnaturally. Let's say I wanted to change this and not talk about completing or not completing the homework, but instead decided to talk about passing the homework or not passing the homework. Well, you could get a score between 0 and 100% on any assignment, so there's a lot of options. However, I could say 0 to 70% is going to be not passing, and 70 to 100% is going to be passing, and so again we could force that into a win or lose, pass or fail scenario. Once you've got that, then you also have to talk about and make sure that the probability of success is the same. It doesn't change for different people. And again, if I'm looking at students who I haven't met yet, it's not going to change. Probably as soon as I meet these students, this starts to become a less accurate model, because once a student completes that first homework assignment, that predicts much, much better whether they're going to complete the second. If you don't complete the first, the odds are not in your favor. And lastly, of course, then we have to be talking about what we're discussing. Here we talked about 0 people not completing the homework, and out of 33 trials. So you have R successes out of N trials. You can do this for all sorts of things. You can do it for homework. You can do it for passing a class in general. You could do it for flu vaccinations. How many people will get them? How many people will be protected? You can do it for what are the chances that our flu vaccine, because most flu vaccines have only 3 viruses that they protect against, what are the chances that those 3 viruses will actually be the ones we see in the wild? So you can do this binomial probability in a lot of scenarios, and this formula becomes interesting. What we've also seen here, and this is a very brilliant idea, is that if you're adding up all of the probabilities from none of the people doing it to all of the people in your trials doing it, those should add up to 1. So if you want to get a large collection of them on one side, sometimes it's easier to subtract the remainders off from the right and do 1 minus some numbers. I also said that's an efficient way of doing it, but possibly for smaller scenarios, it would be beneficial to go into Excel and learn how does the Excel formula work for binomial probability. There's a formula in Excel, and you can find it. We've got a formula sheet for Excel, and I also have some other videos that focus in on specific Excel processes, and you'll see those start to appear on the website. But also, in most statistics textbooks, even to this day, you tend to find charts that start to show different probabilities for different R's, and so then you can just add up. They calculate P of R for you already for some common N, and then you're able to just add those up. I think that just about wraps up this section. Let me, however, take a moment to talk about just a little other things, maybe course management stuff. We're wrapping up binomial probability, which means we're getting ready to wrap up the final steps, I would say, that take us through probability, and now we're about to get ready, as soon as we're done with this section, this chapter, to step out of probability and back firmly into the land of what I would call much more pure statistics. We'll use probability as needed to power that statistics, but we'll be much more firmly in traditional lists of numbers and the things that maybe you usually think about of intro stats. Now is the perfect time, especially with me talking about homework, to make sure that you're exhibiting what I call the good student practices. Are you attempting the homework? Are you following the steps? If you notice at the top of this course website, on my website, mattwiley.org, you'll find that I've had a suggested list of outline of times. See how your actual time spent in a week is comparing to that. In particular, let me mention this. Far too often, and I would say maybe this is a much bigger risk for online students, but I think in today's world with so much on the internet, all of us are really online students in some way or another. Far too often, I think students launch right into the homework with the hope that somehow I'll get through the homework and life will be good. Also, I think sometimes some people look at solving homework and they start to say, someone's faster than me, and that person only goes straight into the homework. Students talk amongst themselves. Let me point out some observations to you then about that. There's a couple of schools of thought that discuss how we learn. And one of the biggest, most important aspects of how we learn is getting out of that mindset that you want to compare yourself to other people. It's called fixed versus growth mindset. Now, as soon as I've written these down, I've instantly dated this video because if you've ever studied any sort of population or people theory or organizational behavior or interpersonal relations, you know as soon as someone comes up with a model, someone else starts to break it. So I'm not using this in the, oh, this is the cool passing fad of the moment. I'm using this as a, let's actually think about this. One of these so-called fixed mindsets is this idea that I'm not good at things that take time. And that's a very, very unfortunate thought process to have. It's unfortunate because everything secretly takes time. You just don't notice it. I've made this example lots of times. I even think on these videos, so I'm sorry for a little bit preaching to the choir, but let me point it out again. By the time you have gotten to a college statistics class, you have probably spent over 10,000 hours reading the English language. You've read hundreds, if not thousands of words a day. You can't even drive down the street without seeing billboards that essentially force you to read. It's natural for you to say in your head, I am good at English. What happens is when you don't put that in perspective, you put the period right there at the end. I'm good at English, period, done, okay. It's also sometimes tempting, because it's a badge of honor, I think, for someone like me to sometimes say, and I'm guilty of this a lot, I will misspell words here on the board. I call it board vision or tunnel vision, and you can't see it, and so I'll spell horribly. Eventually I'll notice this, and I'll crack some sort of joke to the effect of, oh, I'm a math person, so I don't English. Neither of those are really fair. The fact is, I'm of course better at English than I am at math because I've done more English over my lifetime. Even me, someone who makes a living out of mathematics, has probably read more English because even as I'm trying to solve equations, notice how much of the board is still English. Plus I'm talking non-stop for, I don't know, 30, 40-minute videos here, quite a bit. So you should say, I am better at English than math because I have spent decades more doing English than math. I've been doing English since I was a small child. I have only been doing math since I first enrolled into K through 12 education whenever we started the math process there. So there's some differences there. That's one thing. So I'm not good at things that take time. The actual correct mental process to do is anything I am good at took time. This is a cliched example, but we all know that Michael Jordan didn't get picked to play basketball at the beginning. He spent a lot of time practicing. If you listen to early Beethoven, early Bach symphonies, if you listen to early Fleetwood Mac albums, if you read J.K. Rowling's first scribblings or read Tolkien's first writings, it was all junk. It wasn't pointless, but it was junk, and I don't recommend reading them unless you are very terribly curious, and I certainly don't recommend listening to the first albums of Fleetwood Mac. It was bad. At one point, Fleetwood Mac actually went on to a goat farm. That was the point they reached. We're going to go to a goat farm to improve our music. Instead, recognize this. J.K. Rowling shouldn't have skipped over the parts where she was writing junk before she managed to create the most awesome fantasy series of the present. Tolkien shouldn't have quit when he was doodling around with languages that didn't really work. But those weren't interesting stories for the most of us to read. You had to progress beyond that. And we're definitely glad that Beethoven continued persevering past his early music stages. Anything you're good at takes time. The problem is you don't give yourself a fair shake. You say, I'm so much better at English than I am at other things. I'm really good at American government. Why? Well, because I live in America and I vote. So when comes time to write down the process of how does the voting process work, it's like you go to a kindergarten school, you walk through the hallways and you find a little thing, you get some punch cards, and probably there's some sort of strange voting machine. Anything I'm good at took time. It's just time that I might not have noticed in other fields. And in math, I do have to notice the practice because it tends to be a deliberate, specific process that we engage in. Not everyone's as lucky as me doing math for a living. So as you're looking at what you should be doing in the class, because now's probably a good time, we're getting ready to look forward to a midterm here, think about, am I practicing enough? Where am I spending the times? Don't compare yourself to other people in the class. In a statistics class in particular, I tend to have students who have taken their first math class at the college level for the first time in 10, 15 years, right next to people who just got out of Calculus 2. So you can't look at the person next to you and say, oh, they go right into the homework and they're great at it and it takes them no time. And here I am trying to do the homework and it's not working, and now the professor's lecturing me on his high horse about, you should be reading the book more. It's all about overall practice, and some of us walk into a statistics class naturally having a lot more practice. In fact, if you look on my website and you carefully look through all the courses I've taken in the About Me section, you'll find that I've actually taken very few stats courses directly. But I've taken a lot of math courses, and that's made all the difference. It was the difference between picking up some stats books, reading them, going and grabbing some stats theorems from some books for graduate stats and saying, yeah, okay, I understand this. I had a context and framework to put it all in. In fact, as you progress further in your studies, and I point this out simply because this is an intro stats class, as you progress further, I promise, the more you learn, the easier it is to learn anything new because you have context to put it in. So if right now you're feeling a little bit down, if it seems like statistics is a complicated, hard thing that's sucking way more than the recommended minimum time on the website suggests out of your life, let me give you just two pieces of advice. Piece of advice one, do consider following the order of the steps I put on the website. Actually sit down, no matter how painful it seems at the beginning, and read the book. It would be like practicing balancing on one toe on one of those little thin ledges before you went riding a bike. It would seem like you're spending time balancing on a little thin board and life is going badly and you fall off it a lot and it's not very exciting. But when you first go to ride a bike, you'll understand a lot more about balance, and so you'll learn to ride the bike faster. You'll still fall, but it will be faster. So consider reading the book, working through the examples, writing them out, calculating the in-book example exercises first, calculating along with me and pausing this video as I do things and saying, why is he doing that? Always ask the question, why? The second thing that I'll say is this, in terms of overall practice. Don't, and I've said it already, but I'm better saying it again, don't compare yourself to other people. You are only competing against yourself. Yes, I know somewhere out there there's the fact that I have to decide whether you demonstrated a excellent, a very good, a adequate, or some less than adequate measure of proficiency in statistics. The letter grades I assign are letter grades you could take anywhere, because they're the grades you've earned. But for you personally, while you're progressing through this class, I strongly recommend delete the idea of letter grades out of your head. If you get a good letter grade on something, lovely. That means you put in all the effort you need. If you get a not so great letter grade, say, okay, can I do better next time? And always, of course, go back and review, because if you understand binomial probability, that probably means you understand probability distributions. And if something today was complicated, maybe it's easier to go back. And you'll find as you go back, that also builds confidence, because you see things you've already seen, you see them a second time, and you're like, oh, it suddenly clicks. The light bulb goes on. But I think that's enough preaching and lecturing for today. So, anything I'm good at took time, and I will see you next time as we wrap up this section. And until then, be safe.